Morning, ladies and gentlemen. Is that on? You can hear me in the back? So important lecture today because we are going to be simulating statistics today, which we are going to be doing from now until the last day of the course. But before I get going, the usual announcements page, you know when the project is due. You know that there will be homework assigned tonight. You also know that there's a midterm 2 weeks from now here at this time. I would appreciate if that day you please came promptly so that we can get started. And the midterm is on that day at that time, aside from those who have university accommodations. Administrative, bureaucratic questions, anybody, anything? Its course has settled down. I think it has a rhythm now. There's much less "my kernel has died" on Piazza. Thanks greatly to Sam Lau and others who are working behind the scenes constantly to make sure that it stays that way. All right, so I want to go over briefly where we were last time. We were talking about empirical distribution. Empirical, what's the more common word for that? Observed. Thank you. The observed distribution of a sample. So to get any empirical distribution, you actually have to have data, right? These are not theoretical objects. And so we said that if you have a large random sample, not just large any old sample, if you have a large random sample, then the empirical distribution of that sample is likely to resemble the population from which it was drawn. And we saw several examples of that last time. Where we ended up was we were playing roulette and trying to figure out whether we were going to make money. And the way those two slides are connected is we were actually simulating the roulette game and looking at how much money we made. And we had faith in the answers because we were doing large numbers of repetitions, and so we felt that those empirical histograms were actually reflective of the underlying probabilities. And so I want to quickly go over and just get us back to where we were last time. And you'll recall that we had 38 pockets in a roulette wheel, numbered pockets with the colors, and we were betting on red, which pays 1 to 1. Somebody remind me what that means? When you say the bet pays even money or 1 to 1, what's the -1? It's the amount you lose if you have bet $1. Yes? If you bet $2, you'd have your loss would be -2. Okay, but these are winnings, net winnings per dollar bet. So the -1 is the amount you lose if the ball falls in a green or black pocket, and the +1 is the net that you will gain if the ball falls in a red pocket. So physically they will be handing you $2, but one of those was already yours. Okay, so we defined the function that just says for each of these colors what are the winnings, and we put those in a table. Nothing random yet. It's still the 38 pockets labeled not only by the color but by what you would win if you were betting on red. And then we okay, so I want to take a look at this. What happened here? Somebody remind me what a sample does. What does it operate on? That you can see. It operates on a table. And what does it do?
Randomly pulls out.
Randomly pulls out. Very good start. Somebody else continue. It randomly pulls out rows of the table. Thank you. We're getting very close. So randomly pulls out rows. One more important phrase. With replacement. Randomly pulls out rows of the table with replacement and returns what? A table. Good. So that's what you're seeing here. And here are all the winnings on red. This is, if you like, our sample of size, how many did I draw? 200. This is a sample of size 200, but you're not interested in the string of 200 ones and minus ones. What you are interested in is a combination of those ones and minus ones, just the sum. How much money did you make? And that's what we simulated. So we put all of this together in the following simulation. So our sample size was 200. I just decided that we were going to do 5,000 repetitions of betting 200 times, finding the net gain on those 200 bets, and then collecting all of the net gains in an array called, well, net gain. So I will pause for a second, take a look at the code. Questions? This is a repetition of something we did last time. Yes? So net gain is an array. If you take a look up there, it's an array that starts out empty. To that array, we append the net gain on every run. So at the end, it will end up as an array of length 200. An array of length 5,000. For each repetition, it will have the amount of money that you made. Each repetition is 200 spins of the wheel, and you getting a total gain. So let's do this one repetition here. Yes, this was 200 spins of the wheel. And this is actually an important point to understand. So spins dot column, 2. So on that one repetition, you made minus $16. That minus 16 would get tacked on to the end of the array. And then you would do that 5,000 times. Okay. So we did that, and we had after a little wait, a histogram of how many numbers? How many numbers are represented in that histogram? A200, B5000. Which? 5,000. There is one net gain for every one of those repetitions, and we talked about the zero not being where you want it to be. Yep, the zero is where you break even. You have less than even chance of making money if you do this. So this is back to where we were before. And so I hope now that you are sort of shying away from the roulette table a little bit. But, you know, there's always this question of, well, I wouldn't do this one game. I would strategize. I would do other bets. Fine, great. Let's do another bet. So what we're going to do now is we are going to bet on the split. So a split is a bet on an adjacent pair of numbers on the table, and the split we're going to choose is 0, 0, 0. Okay? So we are going to bet on these two pockets. What does that mean? That means we win if the ball ends up in either one of those two pockets. All right, ladies and gentlemen, one spin of the wheel. What is the chance that we win our bet? 2 out of 38. 2 pockets out of the 38 equally likely pockets. That's the chance that we win. Notice that is less chance than the 18 out of 38 chance that we had if we were betting on red. So we have a small chance of winning, relatively, and so the casino is kind to us. If we win, it will give us more money than it would for red. So this bet pays 17 to 1. And so we will define a new winnings column, a new winnings function. So on the split, you win $17 if the pocket is either 0 or 0, 0. Otherwise, you win minus $1. You agree? Good function? Okay. So we can now augment our bets table. Same, just 38 pockets labeled by the color, by what you would win if you were betting $1 on red, and what you would win if you were betting $1 on the 0, 0, 0 split. So far, so good? All right, now what we'd love to do is we'd like to compare what happens if we choose one of these games or the other. And so what we're going to do is we're going to spin the roulette wheel 200 times, and we're going to see how much money we make on both of the bets. Right, on the same 200 spins of the wheel, how much money do you make on both of the bets? And then we're going to do that over and over and over again. All with me? So this is basically the same simulation as before, except it has two new lines because we have a new bet. So same sample size, same number of repetitions. Please note, 2 blank arrays to start with, the gain on red and the gain on split. Good so far? Yep. Okay, I don't actually want you to look at this 4 line right now. What I would like you to look at is the body. That body represents what you're going to do for one game. And what are you doing? You are spinning the roulette wheel n times, that's 200 times. You are adding up your winnings on red and assigning that to the name new net gain on red. You are adding up your winnings on the split, and you're assigning it to the name new net gain on split, and then you are appending these 2 arrays appropriately. So I want you to take a look at the body of the for loop there, line by line, comma by comma, and ask if there are any doubts or questions. I think during your project you have come to realize that the commas, the parentheses, the sequence matters. All right, so pay attention now. Getting used to this? Looking okay? Terrific. I am delighted. If at this stage my class seems bored, I've done my job. Okay. So then we have these 2 arrays, and we collect them in a table, and we draw a histogram, and ready to go? All right, so this is going to chug for a while. Here is where you sing the Jeopardy tune. Too late. Okay. I'll let you absorb that for a while. And talk to your neighbor, please, about what you see. All right, ladies and gentlemen, can you see where my cursor is up there? Yes? Okay, on either of the 2 games, are you more likely to make money than lose? What about the blue game? More likely to win, more likely to make money, more likely to lose money? Lose money, because what is telling you that? What feature of the histogram? Okay, so a histogram has 3 features. There's the spot on the horizontal axis, there is the height, and there's the area. What are you looking at to decide that you are more likely to lose than win? The area, that is what represents proportions. Percent, you're looking at the area. You have more than 50% of the blue area is to the left. And if I look at the yellow, well, I mean, just about more than 50% is to the left. Agreed? One of the things, by the way, to note, this is something that, this is an overlaid pair of histograms. And do you recall that when we had overlaid scatter diagrams and overlaid bar graphs, you just had a table with 2 columns, and you called bar graph or scatter as usual, and it did both on the same scale? That's exactly what's going on here. It strikes me that maybe this is the first time I've done this. I'm not sure. Okay, so you are more likely to lose money than make money on both of them. It seems to me, looking at that, and I'll leave my cursor where it ought to be, at the 0 right here, that you are more likely to lose money if you bet on red. True or false? If you bet on red, right, what should you be looking at? If the chance of losing money, it's all of this area, all of this up to here. Yep? That looks to me noticeably bigger than 50%. Just by eye. I'm not doing any calculation. Of course, you could calculate areas and add up by looking at the numbers. If I look at the yellow histogram, it's here. I'm comparing this versus that. I'm kind of off by this bar. It just seems to me that it's less far away from 50%, that area. So there is a difference between the two games. And at this point, one is tempted to play the yellow game, right? More tempted when you note the following. What is the chance of making more than $50? Compare the two games. If you're betting on red, what's your chance of making more than $50, do you think? Pretty darn small, right? I would not say 0. This is an approximation, after all. It's just a simulation. But pretty darn small. You're not counting on making more than $50. What about if you were betting on the split? There's some chance. I'm looking here, and this is some area that is noticeable. There is some chance of making more than $50. So that sends us in the direction of wanting to bet on the split. However, what else are you seeing? Yeah, there's the other side to the histogram, right here. You have a much bigger chance of losing more than $50 as well. So which one you play depends on the amount of risk you want to take. And I will tell you a story now that, we as people who teach probability and statistics teach this all the time to our introductory classes. And one year, the annual meetings, the professional meetings of statisticians in the United States and all over the world was held in Las Vegas. So it's held every year somewhere. This year it was in Chicago. And, thousands of probabilists and statisticians descend on some unsuspecting city. So what happened was this happened in Las Vegas, and for weeks the papers were touting, the statisticians are coming, come, these guys know how to play, come. So people came, the statisticians came, and everybody stood like this behind the table, because all of us have seen these histograms. Nobody was going to play. At the end of the week-long conference, the statisticians were told, thank you for coming, don't come back. Because after all, everybody else was saying, well, these guys know something, they're not playing, I won't play either. This was not good. Right, not good. Now, if you're going to play the standard gambling games, do not play roulette. Let me just do a little calculation for you. So do you remember that on red, the winnings were 1-to-1? And so what I'd like to do is calculate the average that you would make per dollar that you bet, right? So you make $1. What fraction of the time? It's when you get red, right? What fraction is that? 18 out of 38. And the remainder of the time, you make minus $1. Agreed? And you don't need to do this cell to realize that you're going to get plus 18 and minus 20, and your net result is going to be minus. Yep? The minus 2 over 38 that you're going to get is a classic number in roulette. For virtually every bet on roulette, you expect to lose about 5.25 cents per dollar that you bet. Except one bet. It's a special. The line special. 0, 0, 0, 1, 2, and 3. Pays 6-to-1. Don't do it. Don't do it. You expect to lose 8 cents per game. Don't do it. But I want to show you, with the split, we were gaining $17, yes, with chance 2 and 38. And then we were gaining minus $1 with what chance? 36 and 38. Do you see this is 34 here, the plus, 17 times 2, and the minus is minus 36, and so the net is still minus 2 over 38. They're all set up like that, right? Except the line special, which is worse. So, you can't win. If you insist on gambling, try blackjack. You have to be good at counting cards. There is a well-known book called How to Win at Blackjack. It's that simple. The technique isn't that simple. You have to have a good memory. And people, if you play and win too many times, then large people in black suits come and stand next to you, and gradually you find yourself being sort of, ushered out. But that is one in which the theory actually says that you have some chance of making money. These don't do it. Okay, that's quite enough of messing around with gambling games. We have serious work to do. So what I would like to do is point out something that we've done here. The simulations have involved a lot of random selection, because each time we have not been satisfied with 200 spins of the wheel. We have taken 200 spins of the wheel and reduced those to one number, how much you made on that set of 200. Then we've done that 5,000 times. Yep. So we haven't just simulated one sample of size 200. We have simulated a number calculated based on the sample. And that you can do... actually, let me give you some language. So a parameter is a number associated with the population. So if you have the population of all U.S. households, a parameter might be the average annual household income. And a statistic, please note the singular. A statistic is a number that you calculate based on the sample. And sometimes you can use numbers that are based on the sample. You can use statistics to estimate an unknown parameter. And we will do that in our demo. So this is just a terminology slide. I'm going to use these words, and you should know what they mean. All right. So here is a data set that we saw last time. You recall these? United Airlines flight delays, summer of 2015. We've seen these data before, and there's 13,000 something of them. And so what I would like you to do is I would like you to think of these as a population of delay times from which we are going to draw random samples. We did the following last time. We drew a random sample of size 1,000 and then drew the empirical histogram of the sample, and we noted that the empirical histogram looks very much like the probability histogram, and that is why random samples are a powerful tool in making inferences about unknown populations. Right? Okay. What if instead I were not interested in the entire random sample, I just want to know what the median delay is? Right? If I go to the next flight, I have 50% chance that the delay is going to be, less than this. I want to know what the median delay is. Then for all flights, there is this lovely function, np.median, that allows you to figure out what the median delay is. And credit to United Airlines. Right? You're looking at all those large delays, but the median is only 2 minutes. So half of the flights left within 2 minutes. The latest they left was 2 minutes after the departure time. Now, if you actually calculate the percent that left, 2 minutes or later, had a delay of 2 minutes or later, you'll get something a little bit more than 50% just because there were flights that actually had exactly 2-minute delays. Right? So there are ties, and it's always a problem with these percentiles, medians, and so on, where there's numbers that are exactly at that value, and we're not going to worry too much about it. It's a tiny percent. But it's roughly 50% on either side of 2. That's what you've got. Okay? Okay, so this number, if you think of the entire table as your population, is this number a parameter or a statistic? If you think of your entire table as the population, this number is a parameter or a statistic. Look at the code, please. Is there a sample? There is no sample. This number is measured on the population. It is therefore a parameter. You could compute the corresponding statistic. And so notice that that is the median of a sample of size 1,000. Okay? It's different from the parameter. It's not far, but it's not the same. So here's my sample. This is sample of size 1,000. If I run this again, then my statistic will change. This is the fundamental idea in inference. You have a statistic based on a random sample. It could have come out differently because the sample could have come out differently. And a lot of time will be spent on how differently could it have come out. So if I run this again now on my new sample, well, I get something that's equal. And if I do this, so there's my sample, and there's its median, I got 2 again, etc. So what you can see is that as you sample repeatedly, the statistic is different. There's one statistic for each sample that you draw. And they're not always equal to the parameter, the corresponding parameter. This one looks like at least it's close. So if we want to see how close, what are we going to do? I'm sorry? Do it a bunch of times. Yes, do it a bunch of times is formally called simulating the statistic. Yes? And so I just want to, because we are going to be doing this move for different statistics under different situations throughout the term, what I'd like to do is get some formal discussion of what are the steps involved in simulating a statistic. Right? So the first thing you have to decide, this is a number based on a sample, so you have some decisions to make. You have to decide what statistic are you interested in. So I just pulled median out of a hat, but hopefully you will have a better reason than that for picking something that you want to study. You have to decide on your sample size. This is usually determined by resources. I picked a sample size out of a hat, and it was 1,000. So the first thing is set your the constants of your simulation, and that's one is the sample size, and the other one is the statistic. And you simulate the thing once. For that, what do you have to do? You have to draw a bunch of times. You have to draw from your population a bunch of times. How many times? Whatever was your sample size. In our case, it was 1,000. Yep. So that's 1,000 draws right there. Based on those 1,000 draws, you are going to compute the statistic, and you're going to note that down somewhere. That is a single repetition. That already involves 1,000 draws. Now, you repeat this move many, 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 many times. How many times did we repeat it? Anybody remember? We will repeat 5,000 times or something. Yep. So when you simulate your statistic, you're doing a lot of randomization. That's why it takes a while. One sample of size 1,000 gives you one value of the statistic. Then you do that over and over and over again. And so you keep track of how many times, you keep track of your statistic for every single one of these samples. And at the end of that, if you were doing 5,000 repetitions, you have a list of 5,000 observed values of your statistic. And nobody can make sense of a list of 5,000 numbers. And therefore, you do what we've been doing throughout for long lists of numbers, which is you visualize. You put it in a table, you draw a histogram, standard visualization methods, and try to make some conclusion about the statistic. I'm going to pause for a second and ask you to please internalize this sequence of steps such that I should be able to wake you up at 4:30 in the morning and ask you to recite them, and you will recite them and then fall back to sleep. All right? So, because every simulation has these steps, and our class is based on them. All right, so let's actually do this thing. So that is from the textbook, pretty much exactly the slide that I had up there. All right, so what we are going to do is we are going to simulate the sample median, right? Sample size has been picked to be 1,000. Number of repetitions has been picked to be 5,000. Step one in any simulation, develop the body of the for loop. And so what you have to do, you have to take the sample of size 1,000 and calculate the median of the delay column, right? You now know that NP functions operate on arrays, right? Do I have the right thing there? Where's the array? NP.median is operating on something. What's the part of the something that tells me I'm getting an array? Dot column. Dot column returns an array. It's not a table, it's an array. Good. So you get the new median, and then you tack on that you collect the results somewhere. You do that 5,000 times, and then you take a look at the results that you got. And so if I run my sample medians, it takes a while because it's 1,000 draws 5,000 times. That's a lot of draws. All right. Every one of these is a sample median. Some of them are 2, some of them are not. 4,990 rows emitted. Right number of rows emitted? Yes, I now have 5,000 sample medians. I would like to see what they look like. So I will draw a histogram. And they look like this. And so you can see from that the sample median is likely to be close to the population median, but not exactly. And the main thing you can see is that the sample median varies, and this gives you a sense of how much it varies. Right. So if you have a population, you can figure out how much your sample median would vary. There is the underlying question, if you have a population, why are you taking a sample at all? Excellent question. We asked this last time, and it is to understand variability in samples, so that when we just have a sample, we're going to say, well, if we had the population, it would have been that close, right? So right now, we are just really playing a game. All right, questions about the simulation? Because we are now going to do a simulation, a calculation that was actually done in the Second World War. Yeah.
So each line in the new medians, or in medians,
This.
an average of all the medians?
No. This 3 here was the median of the first sample of 1,000 flight delays. I sampled 1,000 flight delays. That was a list of 1,000 numbers. Yes? Python put it in increasing order and picked off the middle one. That was 3. Then we did it again and again and again, 4,999 more times. More questions? I appreciate the questions. It is very, very important to understand what each number represents so that you can do it smoothly yourself. Okay, I think we are ready to do some estimation here. Okay, so Second World War. We don't have Python, but we have people who, know a little bit about how to work with data, and we have planes. The Allies have planes coming at them. And one thing you would like to do is estimate what the other side has that might come at you, right? That way you can prepare. So there is a classic problem which arose at that time, which is estimating the number of enemy warplanes. Now, what are the data? You don't have a lovely CSV file sitting somewhere that you can do read table of. The data are that thing that's coming at you. Okay, look at it. Look at it. You see any data? You got to be faster than that. This thing's coming at you. What are you seeing? You're seeing one plane numbered 14. Yes? And unfortunately for you, you have seen other planes that have come at you as well, and they have different numbers. So the idea is this. If we note down the serial numbers of the planes that we see, and the other side has been organized enough to number their planes 1, 2, 3, 4, up to whatever, maybe by looking at our sample, we can guess what that whatever was. And that is the game that was played, and it was not a game at all. There were people lives at stake. Okay, so when you do an estimation like this, the quality of your estimation and the interpretation of your results stands or falls on your assumptions. Right? It doesn't matter how much computation you've done. If your assumptions are garbage, then there's no point in doing those calculations. So we will start every time with a discussion of the assumptions. The assumptions that we are making are simplifying assumptions that the planes have serial numbers 1, 2, 3, 4 up to n. And that n, so we have a population of serial numbers. That n, that largest one, is our parameter. We do not know it. And the goal is to estimate n based on the serial numbers that are seen on the planes. So now we have to make some assumptions about the randomness. If we're going to use, the methods of probability theory, we have to make some assumptions on the randomness. And the main assumption that was made at the time and that we are going to make today is an assumption that is familiar to you, that the serial numbers of the planes that we see are draws at random with replacement. You can see the same plane twice, from the numbers 1, 2, 3, 4 up to n. Now, obviously, this is a hugely simplifying assumption. However, it's a start. If you can't make an estimate based on these assumptions, you are almost certainly not going to be able to make it based on more complicated assumptions, right? So this is a simplifying assumptions. I would like to say something. Historians now estimate that the other side in World War II had something like about 100,000 planes. And they did not number them 1, 2, 3, 4 up to 100,000. What we are focusing on is one kind of plane, a smaller number, much more likely to have been labeled in consecutive order. Okay? All right. So our goal is to come up with an estimate based on a sample. And I'm giving you a sample. Talk to your neighbor. What might you do? Think about what you're trying to estimate and think about what you might, if these were the planes that you saw. How about 170 for capital N? Does that make sense? It does not make sense. Because why? Because we've already got 285. That's bigger. Right? If we're assuming it's 1, 2, 3, 4 and capital N is the biggest one, then 24 doesn't make sense. Yeah, if you had to pick one of these numbers, which would you pick? 291. Right? The maximum that you see, it seems like a reasonable thing to start with. Now you know that obviously the number could be bigger than that, but there's a question as to whether you should take a number that's smaller. 291 seems like a good guess. Yeah, if you just throw up your hands and say, I'm going to guess something. Okay, so fine, the maximum. And so how close does that get me to the actual number? And these are the questions that will arise every time you make an estimate based on a random sample. Is your estimate close to the parameter that you're trying to get? How likely is it to be close? Right? Those are the two questions that you have to answer. And in order to do this, you will need to know the variability in your estimate. The largest one of a bunch of numbers, what are its possible values? What is it likely to be? To figure that out, you have one of two choices. You can try to calculate the probability and draw a probability histogram. If you are in Stat 88, the ProbStat connector, could you please raise your hand? Okay. So over the past couple of weeks, have you seen problems on, you're picking things and you're looking at the maximum number, rolls of a die, anything like that? Not yet? It's coming. Okay, so these guys who raise their hands will be doing this in their class because mathematically it is entirely feasible to figure out the distribution of what the maximum could be. We here have a computer at our disposal, so we will do what we have gotten extremely good at doing. We're going to simulate and work out what the maximum could be. For the simulation, I need to make I'm just going to pick, supposing the enemy had 300 warplanes, then what's the chance that your maximum looks like this or that. And you can repeat the simulation in your textbook with any other number of warplanes that you wish. So let's do this. So here are just the 300 serial numbers, table, the range 1 to 301. I'm giving you n here. When you use the interact button in your textbook, you can make it 500 or 20 or whatever and see how the estimate varies. Okay, so I'm just going to assume 300 for now. That's what I used to generate the sample that I showed you earlier. Okay, so now the planes are a sample from this, and I'm going to assume, again off the top of my head, that we have a sample of 30 warplanes. Right. By our assumption, they're a random sample drawn with replacement from that table. And so therefore, what method do I use? I use the method that we kindly gives us, a random sample of size 30 drawn with replacement. And then I want the max of that. So I want you to look at that last line of code. Serial number is that table there. After you've done dot sample 30, what object have you got? A table containing what? One column consisting of the serial numbers of the 30 planes that you observed. Yes? And your estimate is the max of those 30 numbers. So you have to extract those 30 numbers as an array, which you do with dot column, and then you take the max. Code seeming familiar? Have you noticed the difference in this course between this week and the previous weeks? There was one method coming at you every lecture, two methods. It was just coming at you. Yes? And now you just use the same methods over and over and over again. And we'll be doing this. There's just one or two, maybe more methods, but we'll be doing this till the end of the class. And you can see that you are all, even if you are feeling a bit frazzled about coding now, you're all going to get eminently comfortable with what is going on in the code. Okay, so here is one set of warplanes and the maximum number. I got 292 this time. Not so far from 300, is it? Just 30 planes. And the maximum is not that far from 300. 297, 289, not so far. Okay, so now I can stand there clicking away, or I can do what? I can draw a histogram. I'll simulate the thing and draw a histogram. We now know how to simulate this thing. So I will set these two constants of the simulation here. You are welcome to set them in any other way. You can also set the total number of planes differently. So I am setting sample size 30, repetitions 1,000. Okay, we start with an empty array of the maximums. We will 1,000 times do the following. Take our serial number table, sample 30 times. Stick that in a table, calculate the max of the sample serial numbers and append it to this array. And then we are going to look at that table of maxes that we got. Okay, so look at the code, please. Questions? So you should now in your mind be able to have a scheme of a simulation. Set up the empty array or arrays to capture the data. Right? Then you have a for loop that has to go for a certain number of repetitions that you've decided. The body of the loop is the key. That's generating one statistic. And then the rest is all display. All right, so here we go. And I have, how many repetitions did I have? I had 1,000 repetitions. I'm happy. I see 10 rows, and I have 990 rows omitted. So I have 1,000 maxima, each of 30 numbers. And they're pretty close to 300. And if I draw a histogram, look at that. Where's the parameter? The parameter is right here. Right? Where are your estimates? Pretty darn close. Even with a sample size of 30. You can increase the sample size and they'll get even closer. Okay? All right. So this is the simulation of one estimate. And what I'd like to do is go back to... Actually, I'll pause. I'll take questions. You see about this estimate? You can see, we talked about this before. It is going to either get the answer right or it is going to underestimate there is no way you're going to get a bigger answer than the actual number, right? So in that sense, you have this little bit of a worry. On the other hand, it's not going to underestimate by much. That's what you're saying here. Okay, I want to take you back to our sample. Okay, any other estimate? So there's not just one way to estimate something. There are many ways you can think about to estimate, and every way has some good features and some bad features. Any other estimate that you can think of? So we use the maximum, yes? And we did not use the fact that we did not use anything about the other numbers other than they were less than 291. Is it sensible to use the average of these numbers? Well, no, it's not sensible to use the average of these numbers. It's kind of the middle of what you saw. You're trying to get at the big thing, right? What are the numbers in the population? The numbers are 1 through n. Yep. About what is the average of 1 through n? Halfway, right? Yes? N over 2, roughly? So if you took the average of these numbers, you don't think it's n, but is it not reasonable to think that it might be close to n over 2? Yes? So then now can you give me a competing estimate? So I'll start you off. Take the average of these numbers. That's close to what? N over 2, you hope. What is it that you're trying to get at? N. So multiply by 2. Take the average of these numbers, multiply by 2. That should get you close to n. Before we actually do that, I'd like to take questions on whether you feel that will actually get us close to n or not. So now, we did medians before, I'm doing means. The population is the number 1, 2, 3, 4 up to n. Yeah? The mean of that is roughly n over 2. It's not exactly, but it's roughly n over 2. So now we have samples. The statistic that I want to look at is the sample mean that should get me close to n over 2, but it's not n over 2 that I want, it's n. So I want twice the sample mean. That's my estimate. Yes?
I have a question for 300, and if this is similar, why couldn't you make it, like, say you missed 3, 4, 500, and like there were 500 rest? I don't understand why 300.
So why 300? Because I picked it, as I said, the code is available for you, and I would like you to change that number and see how the estimate changes. So we have a new our largest serial number was likely to underestimate, so we're going to try another one that is 2 times the average. And I will run the simulation since you seem to accept that we are going to have twice the average. So now, we're going to compare 2 statistics, the max and twice the average. I therefore have to start with 2 empty arrays. So for every one of 1,000 times, I am going to sample 30 times. Yep, same as before. I am going to calculate the max of the sampled numbers and append the max array. I am also going to calculate the mean of the sampled numbers, multiply by 2, and collect in twice average. I will pause for 30 seconds. The heart of the simulation is right here. Draw your sample, compute your statistics, collect. And then we will take a look at the results, and the results look like this. Okay? You've got one set of estimates and another set of estimates. And, well, you can see this one overestimates. Right? If your average was closer to 300 than to 1, you will end up overestimating. And so now if I look at the histograms, the 2 have distinctly different behavior. Yep. The blue one, the max, is our old friend that either gets the answer right or underestimates. The new one could overestimate and underestimate by about equal numbers. right? So in that sense, it has what we call less bias. It's not systematically underestimating or systematically overestimating. However, it can give you a number that's too big. So which one you use is really a question of your utility, right? If you underestimate, you might suffer losses because you haven't accounted for the things that are coming at you. If you overestimate, you might be putting resources to defend against planes that don't exist. So you might be taking away resources from everywhere, from somewhere else. And so I want to leave you with a little message here. Bias. One of our estimates is bias. Yes, it typically underestimates. Systematic error in one direction. Variability. One of our estimates is low in variability, the other one's high in variability. Yes? You want low bias and low variability. You want an estimate that's really tightly clustered around the thing that you're trying to estimate. Yes? Do we have one like that? We have what is called the Bias-Variance Tradeoff. Our max has low variability, but it is biased. Agree or disagree? Yep. So the good, it's low variability. Bad, it's biased. Twice the average, low bias. Excellent, highly variable. Bad, because it's far away from the